Okay, there are a lot of different approaches to gradual typing around these days, all seemingly different. So how are we to make sense of this space? Well, the research community has come up with 3 semantics to capture the key differences between most of these approaches. The Erasure semantics, championed by industrial systems, uses types for type checking and then throws them away to run the program as if it were fully untyped. Thus, any mismatches between type annotations and actual values not caught statically manifest as errors from the runtime, accompanied only by a stack trace to help developers track down the mistake. The other 2 semantics come from the academic world, and they try to help programmers by inserting dynamic checks to verify that values match up with annotated types. Furthermore, the semantics offer special failure information called blame that identifies parts of the program as being related to the type-value mismatch. That said, the 2 semantics perform the dynamic checks differently and provide very different kinds of blame. In the face of these 3 semantics, I want to pose a research question. How do these semantics help programmers find the source of type-value mismatches? Of course, this question has been investigated before. From extensive theoretical work developing and analyzing the semantics, we've learned that the semantics offer different kinds and degrees of guarantees for detecting type-value mismatches and for blame. But it does not tell us exactly how these guarantees translate into practical benefits for the working programmer. Then, extensive performance work has shown how those guarantees come at sometimes extreme performance penalties, but not whether the costs are justified by debugging benefits. There's also been a little work analyzing user preferences, which suggests that users prefer semantics with stronger guarantees. But of course, it's not clear how general that preference is. This work develops a new method called the rational programmer, which taps into aspects of all 3 of the other approaches that we've just seen. The key idea of the method, inspired by the economic idea of Homo economicus, is to simulate an idealized programmer using a system in real-world conditions. By testing the simulation in a large and varied set of situations, we can understand the pragmatic strengths and weaknesses of a system. To make this concrete, the rational programmer for gradual typing will simulate a programmer with a gradually typed program that, when run, produces a type-value mismatch error, and will try to use it to locate the source of the mismatch in the program, using blame or whatever other information is available. Specifically, the simulation will follow an algorithm that looks like this. First, it will run the program to get a type-value mismatch error. Then, it will identify the blamed module. Next, it will type the blamed module. And finally, it will type check the program. And if it gets a type error, then the algorithm terminates, and we say that it succeeds at locating the mismatch. Otherwise, it goes back and continues from step 1. And if it doesn't eventually get a type error, then we'll get stuck there here, trying to type the blamed module, perhaps because it's already typed, as we'll see later. If this happens, the rational programmer fails to locate the mismatch. And so these 2 steps form the possible success and failure termination conditions for the simulation. Now, using this simulation, we can design an experiment to evaluate how often the rational programmer succeeds at locating the source of type-value mismatches in a corpus of debugging scenarios from real programs. The experiment essentially consists of running the rational programmer on all of the scenarios and collecting its successes and failures for analysis. Of course, there are 3 different semantics that we want to analyze, so we run this experiment on 3 versions of the simulation using each of the 3 semantics, which we call modes. And then at the end we can compare the success rates of each mode to understand which semantics offers more useful information for the rational programmer to locate the source of type-value mismatches. And we'll do all of this in the context of Racket, using implementations of all 3 semantics based on typed Racket, and using debugging scenarios from typed Racket programs. But before we get into the details of the experiment, let's get some intuition for how the rational programmer works with each of the 3 semantics through an example. Here's the dependency graph of a card game program, which has modules defining components of the game like players, cards, and the dealer. And these 3 modules are typed, and the rest are untyped. To start a game, the main module creates a bunch of player objects and sends them over to the dealer to manage the game. The dealer module expects the players to have a start turn method, and throughout the game it iterates over the players to call that method on each one. And the player module defines the player class, but it has a mistake. The start turn method is misspelled. In other words, there's a mismatch between the player type that the rest of the program, and especially the dealer, expects, and the actual player values that the player module will produce. So let's see how the rational programmer will locate the source of that mismatch in this program by making those expectations manifest through type annotations. We'll start with the natural mode. When we run the program under the natural semantics, we get a contract error, which blames the player module. So the rational programmer will type the player module as a way of checking the expectations about its interface, and then the type checker can detect the mismatch and raise a type error. So the rational programmer succeeds using the natural semantics. Next, let's see the erasure mode. Running the program under the erasure semantics produces an error from the runtime, saying that there is no method named startTurn, and the stack trace identifies that the error happens in the dealer module. So the rational programmer will treat this as a kind of blame, and it will type the dealer module. The program still type checks, so the rational programmer runs the program again, and it gets the same error. And now it's stuck, because both of the modules identified in the stack trace are already typed. So this mode of the rational programmer fails to locate the source of the mismatch. Alright, finally, let's see the transient mode. Running the original program under the transient semantics produces the same error from the runtime as we saw before. So the rational programmer will again identify the dealer module from the stack and add types to it. Now the program has enough types that when run, it produces a transient assertion failure, which blames the player module. After typing it, now the program fails to type check, and so the rational programmer succeeds using the transient semantics. So now we've seen how the rational programmer simulation distinguishes between the information each of the semantics offers for locating the source of type value mismatches, and I want to make an observation, which is that blame seems to have been useful. Both the natural and transient modes were able to use blame to successfully locate the source of the mismatch in the example. But was blame really necessary for the rational programmer to succeed? In particular, both of these semantics provide blame in addition to dynamic checks, and it isn't clear if we can attribute the success to the blame alone. To understand this distinction, we can create new modes of the rational programmer, which use the natural and transient semantics, but ignore blame and instead just use the stack traces from check failures, and we can see how often these modes succeed compared to the modes that use blame, to tease apart the value of blame from checks alone. And in fact, this way of using modes gives us a very flexible way to add baselines and control for confounding factors in our experiment. We actually use even more modes in the paper to do things like analyze different ways of interpreting blame and comparing against the effectiveness of using a totally random debugging strategy. I won't get into the details for the sake of time though, so check out the paper for more. And now, before wrapping up, I want to quickly return to the experiment. So here's what we did. Starting with 10 typed racket programs from the GTB benchmark suite, we used mutation to create about 72,000 different debugging scenarios. And then we ran all the modes of the rational programmer on all of those scenarios, which took about 3.5 years of compute time total. Finally, we analyzed and compared the success rates of the different modes. Again, for the sake of time, I won't go into more detail about the experiment or analysis, and I'll just give a few takeaways. First, natural blame leads the rational programmer to success in about 90% of the scenarios. That said, natural blame only provides more useful information than transient blame in about 4% of the scenarios. And finally, Erasure provides enough information for the rational programmer to succeed in almost 80% of the scenarios, despite not having any checks or blame at all. In closing, though, I want to step back and look at the big picture. The rational programmer is a new method for understanding the pragmatics of systems like gradual typing, and in this experiment it has given us a new lens into the pragmatics of debugging with the 3 different semantics. And overall, we think this experience has shown how the rational programmer is a useful tool to add to the toolbox of the working PL researcher. Thank you.